So in physics today, we're going to start looking at current electricity. So an electric current consists of moving charges. Therefore, electricity is the flow of electrons in a conductor. And for us to understand current electricity, it is important to look at different electrical symbols. So the first symbol that we're going to start with is that of a wire. So the wire is written in this form, and the function of wire is to pass current very easily from one part of a circuit to another. So that's the function. Then we're going to look at the cell. The function of the cell is to supply electrical energy, and the cell has a large terminal which is on the left, as you can see, and that represents the positive charge. So this large terminal represents the positive charge, and the smaller terminal represents the negative charge. Let us look at the battery. So the function of the battery is to supply electrical energy, and the battery is more than one cell, or a battery is made up of two or more cells. So that's the battery. Let us look at DC supply. So the DC supply supplies electrical energy, and DC stands for direct current. So for DC, that means current always moves in one direction. So for direct current moves in one direction. Let us look at AC supply, which is alternating current. So that's the symbol, and the function of AC supply is to supply electrical energy, and AC stands for alternating current. So this current continues changing direction. So it does not move in one direction, but it continues to change direction. Let us look at the fuse. So that's the symbol of the fuse. So a fuse is a safety device which will blow or melt if the current flowing through it exceeds a specified value. So a fuse will melt once current exceeds a certain value. Let us look at the transformer. So that's the symbol of the transformer. So the two coils of wire linked by an iron core. Transformers are used to step up, increase, or step down or reduce AC voltages. So the transformers are used to increase or reduce the voltages. Let us look at the symbol of the lamp. So the function of the lamp is to convert electric energy to light, and the symbol is used for lamp providing illumination. For example, a car headlamp or a torch lamp. So the function of the lamp is just to convert electric energy to light. Then this type of a lamp is that of lightning. So it is lightning. Then there is also another type of lamp which is an indicator. So the symbol of this is in this form. So also the function of this is to convert electric energy to light. Let us look at the symbol of a heater. A heater. So that's the symbol of the heater, and the function of the heater is to convert electric energy to heat. Let us look at the motor. So the function of the motor is to convert electric energy to kinetic energy. Let us look at the resistor. So this is the symbol of the resistor. So a resistor restricts the flow of current. For example, to limit the current passing through an electric appliance. So this resistor restricts the flow of current. For example, to limit the current passing through an electric appliance. So that's the resistor. Then let us look at the variable resistor, or which is also referred to as the rheostat. Which is also referred to as the rheostat. And the symbol of this So the variable resistor, this is the type of variable resistor with two contacts. It is also referred to as the rheostat. It is usually used to control current. So that's usually used to control current. So those are some of the symbols that we use. So we continue looking at the symbols that are used in an electric circuit, and today we're going to look at the symbol of the voltmeter, ammeter, and the galvanometer. So we have the voltmeter. So this is drawn in this form, and the function of the voltmeter is to measure voltage. Then we also have the ammeter. This is drawn in this form, and the function of the ammeter is to measure current. We also have the galvanometer. We also have the galvanometer, and this is drawn in form of an arrow. So you have an arrow there, and the function of the galvanometer is to measure tiny current, and this is a very sensitive meter. So those are some of the symbols that we used in an electric circuit. Let us look at current. So we represent current by I. So you're going to discover that in most of the books they represent current by I there. And the definition of current is defined as the rate of flow of charge. So this is the rate of flow of charge. So current is defined as the rate it's defined as the rate of flow of charge. And the formula that we can use, we can say our current, which is I, is equal to Q, which is charge over T. So we know that from this formula, I, that's current, then Q, we know that that's charge, then T, that's time, and the units of current there, it's in amps, then there it's coulomb, then there it's seconds. So we can say that the units of current is amp, which is represented by A, and the instrument that is used to measure current in a circuit is ammeter. So we use the ammeter, and the ammeter is connected in series in an electric circuit. So we connect the ammeter in series. So you need to take note of that. So if we draw the connection of the ammeter, we take, for instance, this is our lamp, then Then we have a cell here. Here we can say we can put our ammeter here. It must be connected in series, and you must note that the positive side of the ammeter must be connected to the positive side. So as we know, this is the positive, so the positive must be connected to the positive, and the negative must be connected to the negative. Let us look at current electricity. Not the current electricity, sorry, but quantity of charges. So let us look at quantity of charges. We know that current electricity, this is the type of electricity which involves the flow of electrons or charges that are in motion. So this is just the flow of electrons or charges, that's current electricity. So for us to look at quantity of charge, it's very, very important to know the charges. So the amount of charge flowing through the circuit is referred to as quantity of charge. So quantity of charge, this is the amount. So this is the amount of charge flowing through the circuit. That's a quantity of charge. And the symbol of charge, the symbol that we use to represent charge, it's Q. That's the symbol. Then the SI units of charge, it's a coulomb. That's coulomb, which is represented by C. So the units that we use to represent charge, that's coulomb, and we use it and we represent it by letter C. Then the other thing that you need to know, that the formula that we use when finding charge. So from the previous discussion that we had, we said that current is equals to charge divided by time. So for us to find Q there, we are going to multiply time and current. So that's going to be current multiplied by time. So that's the formula that we use. Let us look at some of the examples. So for the first example, if the current through the circuit is 5 amps, what charge passes in 10 seconds. So that's the first question. If the current flowing through the circuit is 5 amps, what charge passes in 10 seconds? So here the current we have been given, so current which is I, we have been given, which is 5 amps, and the first question asks us to calculate current passing in 10 seconds. So from this you can collect your data. You know that current, that's 5 amp. You also know that time, that's 10 seconds, but Q you don't know, which is charge. So we know that Q is equal to IT. Q is equal to I, that's 5, multiplied by T, that's which is 10. So there Q is equal to, there our Q is equal to 50. Let us look at another example. So that's 5 coulomb. Let us look at another example. So if we have this situation, so we know that the current that we have been given is 5, but which is passing through the circuit 5 minutes. So note that the time we have been given in minutes, but the time must always be in seconds. So our time must be in seconds. So for us to calculate charge there, we're going to collect our data. And our data, we know that our current, that's 5. We also know that time, that's 5 minutes. But we know that the units of time must be in seconds. So here we know that 1 minute is equal to 60 seconds, and we have 5 minutes there is equals to x. So our time there in seconds, 60 multiplied by 5, that's 300 seconds. So we know our time there. So that means we can calculate charge. So charge there is going to be Q is equal to current, that's 5 multiplied by 300. And when we multiply that, our current is going to be 1500 coulomb. So that's how you can calculate charge. Let us look at a different situation. So for another example, and this example reads, calculate the amount of current if 144 coulomb of charge flows through a point in 30 minutes. So calculate the amount of current. So we're supposed to calculate current. So this is example 2. If the charge that we have been given is 144 coulomb, then it passes through a point in 30 minutes. So from this information, we know that our time here must always be in seconds. So the first thing is to convert that in seconds. So we know that 1 minute is equals to 60 seconds. What about 30 minutes is equal to x? And if we multiply there, x is equals to 60 multiplied by 30, that's 1800 seconds. Since we know our time in seconds there, we can calculate current. So we know that current is equals to Q divided by T. Current is equals to our charge there, it's 144 coulomb divided by our time there, it's 1800. So to calculate current there, we'll say current is equals to 144 divided by 1800. The answer there is 0.08 amp. So those are the types of calculations. Where you have questions, you can ask in the group. So the direction of current. So before electrons were discovered, it was assumed that current was the flow of positive charges. That means that we actually assumed that that was the movement from the positive charges to the negative charges. And after electrons were discovered, we now know that current is the flow of negative charges. So it moves from the negative to the positive. Although we still ignore this same concept that current is the movement from the negative charge to the positive, we still assume that current is the movement of positive charges from the positive to the negative, and that is what is referred to as convection current. So we still assume that current moves from the positive terminal here, it goes until it reaches the negative terminal, and that is what is referred to as convection current. And we can say that the direction of electrons, they will move from the negative. So as you can see, these arrows, they'll move from the negative until they reach the positive. So that's the direction of current. Let us look at potential difference. So potential difference is defined as the work done in moving one coulomb of electricity between the points. So this is the work done in moving one coulomb of electricity between points. So this is defined as the work done in moving one coulomb of electricity between the points. That's the definition. And the symbol of potential difference, the symbol that we use is PD. That's the symbol. Then the unit of potential difference, the unit, that's volts. So we use the volts, and the volts are represented by V. Then the other thing that you must know on potential difference is that potential difference is also called voltage. So the other name of potential difference is also called voltage. And you must know that 1 volt, which is 1 V, is equal to 1 joule, 1 joule, which is 1 per coulomb. So 1 volt is equals to 1 coulomb per 1 joule per coulomb, and we know that joules, these are the units of energy, and coulomb there, that's the units of charge. Let us look at some of the examples. And for the first example, it reads, if 6 joule the first example reads, if I have 6 joule which is transferred when 2 coulomb passes, what is the potential difference? So from the data, so the first question, so 6 joules transferred when 2 coulomb passes, what is the potential difference? So from this, I know that the energy is 6 joule, then the charge, which is Q, is 2 coulomb. Then have been asked to find the potential difference, and from this I can say potential difference is equal to my energy, which is represented by W or E, so W divided by Q. So my potential difference will be equal to there W, that's energy, which is 6 divided by Q, that's 2. So my potential difference there, it's 3 volts. Let us look at another example. In 20 seconds, a charge of 25 coulomb leaves a battery, and 200 joules of energy are delivered to an outside current as a result. Then A, what is the potential difference across the battery? So this is 2. So in 20 seconds, so time have been given as 10 in 10 seconds, sorry. In 10 seconds, a charge of 25 coulomb leaves a battery. So a charge of, we know that our charge there, which is Q, we have been given as 25 coulomb, leaves a battery, and 200 joules and 200 joules of energy are delivered to an outside circuit as a result. So here we know that our energy is equal to 200 joules. As a result, what is the potential difference across the battery? So we need to find our potential difference. So we will say potential difference is equal to energy divided by charge. You can represent it by W or E. So potential difference is equal to 200 divided by 25. So my potential difference there, 200 divided by 25, that's 8 volts. So that was A. Let us look at B. The current flows from the current flowing through the battery. So we need to calculate current. So B requires us to calculate current from the same information, and from this information we can collect our data, and we know that time have been given as 10 seconds, Q have been given as 25 coulomb. That means that we can calculate current with those information. So current is equals to Q divided by charge divided by time. So the charge there is 25 divided by 10, and current there is going to be 2.5 amps. So that's the current. That's the potential difference. Where you have questions, you can ask in the group. So the electromotive force, let us look at the definition of the electromotive force. So this is defined as the total work done by a source of electricity in driving 1 coulomb of electricity through the circuit. So this is the total work done by a source of electricity. So you need to differentiate between the electromotive force and the potential difference. Potential difference, we said that was the work done in moving 1 coulomb of electricity between 2 points. But electromotive force is defined as the total work done by a source of electricity in driving 1 coulomb of electricity through the circuit. And the symbol that we use to represent electromotive force, so the symbol that we use is EMF. That's the symbol that we use. Then the units of electromotive force is volts. So the unit we use. Then the other important thing that must be known is that sum of the potential difference gives the electromotive force. So the sum of the potential difference gives the electromotive force. So that's all about the electromotive force. Where you have questions, you can ask in the group. Then let us look at electrical energy. So electrical energy is defined as the work done in moving a quantity of charge. So this is the work done in moving a quantity of charge. Moving a quantity of charge. That's the definition. The symbol that we use to represent electrical energy is E or W. The symbol that you use in some books you're going to find E, in some books you're going to find W. Then the units of measuring energy is joule. The joules. So the units given in joule, which is represented by J. That's the units. Then let us look at the formula. So the formula that we use, we're going to say E is equal to Q multiplied by V. Q, we know that that's charge, and V, that's voltage. That's our potential difference. That's our voltage. Then we can proceed. From this definition, we can also write up different sorry, from this formula that I've given you, you can also write other formulas. So we're going to say our energy is equals to, we know that Q can be broken down into current multiplied by T. So we can also say that it is equals to V by T. In some cases, we can also say E is equal to, so there we can break down this V. When we break down V, we know that V is defined by saying current multiplied by resistance. So we're going to have current, resistance, then have IT, then we're going to have, since the current two, so current squared, then have RT. So that's the other formula that you can use. And the other formula that you can use is this one. You say energy is equals to power multiplied by time. You're going to say power is equal to voltage multiplied by current. So from here, we can put our P multiplied by T is going to give us our energy. Let us look at some of the examples. So we continue looking at electrical energy, and today we're going to look at some of the examples under electrical energy. And the first example reads, the PDF across the lamp is 12 volts. How many joule of electrical energy are changed into heat and light when? So I've been given two instances. I've been given so from this question, this is an example. I've been given potential difference, which is volts. I've been given as 12 volts, and A reads a charge of 5 coulomb passes through it. So a charge of 5 coulomb passes through it. So I'm required to calculate electrical energy, and from this data that I've been given, I can say electrical energy is equals to QV, and I know my Q, that's my charge. So I know that's 5 multiplied by the voltage, that's 12. So 5 multiplied by 12, that's 60 joule. So that's my answer for A. So let us look at B. B reads a current of 2 amps flows through it for 10 seconds. So I've been given a current of 5 amps flows through a current of 2 amps, a current of 2 amps flows through it for 10 seconds, and time I've been given as 10 seconds, and I know that my voltage is equal to 12 volts. So from this information I can use this formula. I'll say energy is equal to voltage multiplied by current multiplied by time. So energy is equal to my voltage, that's 12, multiplied by current there, that's 2, multiplied by 10, which is time. So the energy there is going to be 12 multiplied by 2 multiplied by 10, that's 240 joule. Let us look at another example. So example 2. Example 2 reads a current of 5 amps flows through a 4 ohm resistor in 20 seconds. How much thermal does the resistor give off? So from this question, I've been given as current, I've been given as 5 amps. Then the resistance have been given as 4 ohms. Then I've also been given time, which is 20 seconds, and I'm supposed to calculate how much thermal the resistor gives off. So from this information I can use this formula. I can say energy is equal to I squared RT, and my electrical energy is going to be current, I know that's 5 squared, resistance I know that's 4 multiplied by 20. So when I do my multiplication there, it's going to give me 2000 joule. Let us look at the factors which affect electrical energy. So the factors which affect electrical energy, and the first factor we can say the amount of current flowing. So the amount of current flowing is the first factor. The second factor we can say time taken, and these factors they all come from the formula. And the other factor you can say potential difference, and the other factor we can say resistance of the conductor. So resistance. So these are the factors that affect electrical energy. Where you have questions, you can ask in the group. Let us now look at power. So power is defined as the rate of doing work. This is defined as the rate of doing work. That's the definition. So power is defined as the rate of doing work. Then the symbol of power is P. The symbol that we use is P. Then the SI units of power can either be joule per second, which is also called watts. So the units of power, you can either write joule per second or watts. So that's the definition, the symbol, and the SI units of power. And from this definition, we can say power is equal to work done divided by the time taken. And work done here, it can also work done can also be referred to as energy. So it can be energy over time taken. Then let us look at the formulas that we use. So the first formula that you can use, you can say power is equal to current multiplied by voltage. The other formula that you can use, you can say power is equal to, so we can change this. So when we change current, it's going to be voltage divided by resistance multiplied by voltage. So power is this squared divided by resistance. So that's the other formula that you can use. The other formula that you can say power is equal to current squared. So from this, let us come back to this one. So for us to get, we know that power is equal to by voltage. We know that power is equal to current. And this will changed. Voltage is found by saying current multiplied by resistance. So their power is equal to current squared resistance, which is the same as this one. Let us look at another formula. So the other formula that you can use is the one that is from the definition states power is defined as the rate of work done, and we know that work can also be energy, so we can say energy divided by time. These are some of the formulas that you can use when finding power. And let us look at some of the examples. The first example reads, an electric pressing iron is rated at 220 volts and 1100 watts. Calculate the current it takes and the resistance of its element. So an electric pressing iron is rated at 220 volts, 1100 watts. Calculate the current it takes and the resistance of its elements. So let us look at the data. So this is example 1. Example 1, we have been voltage is 220 and we have been given power as 1100 watts. We have been told to get current and resistance. So for us to calculate current there, we know that power is equals to voltage multiplied current. Then power have been given as 1100 is equal to voltage given as 220 divided by current. So calculate current there by 220 divided by 120, and my they are going to be equal to 5 amps. So that's my current there, and since I know my current, I can calculate the resistance. So the resistance, we know that is equal to voltage divided by current. Voltage, we know it's 220 divided by the current is 5. So resistance will be equal to 220 divided by 5. That's 44 ohms. So that's 4 ohms. The other question reads, what is the power of a ramp rated at 12 volts 2 amps? So we need to calculate the power from a lamp that is rated volts and 2 amps. And from this we know that power is voltage multiplied by current. So is equals to voltage there is 12 volts multiplied by our current there is 2. So power is equal to 12 multiplied by 2, that's 24 watts. You can say power is equal to 24 joule per second. Let us look at electrical resistance. So this is defined as the measure of the opposition to the flow of an electric current in a conductor. So this is the measure of the opposition to the flow of an electric current in the conductor. And resistance is the ratio of voltage to current, which is constant. Then the symbol of resistance is R. So here the symbol for resistance is R. And from this we know that the SI units of resistance, so the SI units for resistance is ohms, is given by this symbol. Then let us look at Ohm's law. So the law states that the current flowing through a conductor is direct proportion to the potential difference across it, provided temperature is kept constant. So that's the definition. The law states that the current flowing through a conductor is direct proportion to the potential difference across it, provided the temperature is kept constant. And if we try to write that expression that is showing current flowing through the conductor is direct proportion, we can say is direct proportion to current, and that the voltage is equal to our constant multiplied by our current there. And from this, find K, we're going to divide by current divided by current. You can say K is equal to voltage divided by current. So we say voltage divided by current, and that K is what is resistance. So resistance is K, and we write our formula for resistance. We say R is to voltage divided by current. And since we have said that Ohm's law states that the current flowing through the conductor is direct proportion to the potential difference across it provided temperature is kept constant. So if you draw your graph, when you plot and your potential difference, your graph will appear in this form. So we're going to have this slope, and this will be like a straight line. And here you need to put your current, and you need to put your potential difference. This will give you this slope. And if you calculate your resistance across this graph is constant, your resistance must be constant. Let us look at the factors which affect resistance of a conductor. The factors which affects resistance of a conductor. So some of that affect the resistance of a conductor: we have temperature, we have length of the conductor, we have the cross section, which is also referred to as the thickness of a conductor. We also have the type of material. So those are the factors which affect resistance. So for temperature, so when temperature increases, resistance will also increase. So an increase in temperature will also mean an increase in resistance. And when temperature is reduced, so when T is reduced, you reduce it, resistance is also going to increase. Then the other factor that affects is the length of conductor. So when the length of a conductor is increased, resistance is also going to increase. So an increase in length, that is going to mean that there will be an increase in resistance, and a reduction in the length of the conductor, that means resistance is also going to be reduced. Let us look at the other factor. I don't know, I'll just write here the cross section or thickness of conductor. So thickness of conductor. So if the cross section is increased, or if the thickness is increased, resistance is going to reduce. So here this means that if the increase here in thickness, we see which is thickness, we increase thickness here. If we increase thickness, that means our resistance here is going to reduce. And if there is a reduction in thickness, our resistance is going to increase. Then if we look at the other factor, which is the type of a material, so the other factor is the type of material. So some materials have less resistance than others. And if you look at silver has free electrons, and this means that it is a very good conductor. And silver has a less resistance due to that, because it has more free electrons. So we have silver, and if we compare silver with copper, copper does not have more free electrons than silver. So that means that resistance in copper is higher than in silver. So those are the factors that affects resistance, and we have also looked at resistance. Where you have questions, you can ask in the group. So we continue looking at electricity, and today we're going to start with a circuit. So a circuit is defined as a path between two or more points along which electric current can be carried. So this is just a path through which electric current can flow. So this is the path through which electric current can move from one point to another. And another circuit, we're going to look at types of connections. We're going to look at a series connection. Also going to look at a parallel connection. So let's start with a series connection. So a series connection is a type of connection in which the current is the same throughout each component. So this is the type of connection in which current is the same through components. So that's the definition of a series connection. For example, if you have some lamps that are connected in series connection, they will appear in this form. So for example, if we have these two lamps, as you can see, these two lamps are connected in series, and we have ammeter. That's an example of a series connection. And let us look at some of the rules of series connection. So the rules of series connection, important to know the rules of the series connection. And the first rule states current flows in one direction. So if we check out here on the table, here current will be moving from positive, it will be going this side. So as you can see, it will be moving in one direction, it won't be moving in two directions. So that's the first rule. So current moves in one direction. Second rule states current flowing across each component is the same. So this means that if current this this ramp A is 4 amps. That means that even the current that is flowing through lamp B will be 4 amps. So the current flowing through each component is the same. So current flowing through each component Let us look at another rule. The rule states that the potential difference across each resistor differs if the values are not the same. So if we have some, if we draw this circuit, if we draw this circuit and we have resistors here and having two different values, and we say if this is 2 amps, 2 ohms, sorry, and this is 4 ohms, this means that the potential difference that will be flowing through these two resistance will be different. So the potential difference across each resistor differs. The potential difference across each resistor differs. Then the other rule states the sum of the potential difference across each component gives the total voltage. And this total voltage, we say that's the electromotive force. So the sum of the potential difference across each component, and if we assume that, if we just assume that the voltage here is 6 volts, and here the voltage we are just assuming is 3 volts, that means that the sum of the potential difference across each component gives the total voltage. So here to calculate our total voltage, we're going to say Vt is equal to 6 plus 3, and that's going to be 9 volts. And since we have 9 volts, we can say our electromotive force is equal to 9 volts. So the potential the sum of the potential difference across each component gives the what? The electromotive force. So the sum of the potential difference across each component gives the total voltage, the total voltage, and this total voltage is the electromotive force. Then let us now look at on how you can calculate the total resistor in a series connection. So calculating total resistance in a series connection. So for you to calculate the total resistance in the series connection, say your total resistance is equal to resistance 1 plus the resistance 2 plus the resistance 3, and you can go on depending on the number of resistors you have in the circuit. So that's the formula that we use. Let us look at just a simple example. So if we have this type of circuit and we have 3 resistors, we have 2 ohms here, we have 3 ohms, and we have 4 ohms, and you have been told to calculate the total resistance for the circuit. So we're going to say total resistance is equal to resistance 1 plus resistance 2 plus resistance 3. So there we're going to have 2 plus 3 plus 4, and I'm going to answer that 9 ohms. So that's the formula that we use. Let us now look at on how you can calculate the total voltage. So the total voltage, which is referred to as the electromotive force. So for us to calculate the total voltage, we know that voltage across each component or each resistor is not the same. So we can say our total voltage, you can say you need to add voltage 1 plus voltage 2 plus voltage 3. And since we know that the formula of calculating voltage here, it's a current multiplied by the resistance. So here you can current multiplied by 1 as current multiplied by resistance 2 plus multiplied by resistance 3. So that's the formula that we use. Then for this okay, then from this we know that here the current is always same, and we can use this example here. For example, if you have been told that the current that is passing through this circuit is 1 amps, so the current is read as current that is flowing through this is 1 amps, and you have been told to calculate the total voltage. So here we are going to say we know that our resistance 1, that's 2, our resistance 2, that's 3, our resistance 3, that's 4. So here we are going to say our current is the same. We're going to say 1 multiplied by 2, which is the resistance 1, plus we're going to say 1 multiplied by our resistance 2, which is 3, plus is the same. We're going to say 1 multiplied by 4. And if you find your answer, this will be volts. So that's the formula that you use. And total, we know that total voltage is also referred to as electromotive force. So you can also say our electromotive force there, it's 9 volts. Let us now look at parallel connection. So for the parallel connection, this is the type of connection in which the current takes more than one path. So it does not take like one path that we describe in a series connection. In series connection, current takes one path, but here it takes more than one path. And for example, if we draw two lamps that are connected in parallel connection, they will appear in this form. And when put ammeter there, so as you can see, this is an example of a parallel connection. So current here, it will be taking two directions. So when it comes here, one of it will branch, it will go this side, then the other one will go there, it will go that side. So that means their current will be taking two directions. Then let us look at some of the basic rules in parallel connection. So the rules. So the first rule states the flow of current takes more than one path. So the flow of current takes more than one path. So the flow of current takes more than one path. Then the other rule states the current entering the parallel connection is equal to the current leaving the parallel connection. So the current that is entering the parallel connection is the same as the current that is leaving the parallel connection. Same to the current leaving the parallel connection. Then the other rule that you need to take into consideration, the potential difference is the same across each resistor. So here the potential difference is always the same. So you can say PD is the same. So those are some of the basic rules under parallel connections. Where you have questions for everything that we have done, you can ask in the group. So let us now look at some of the calculations in a parallel connection. So the first thing that we said under parallel connection, we said that the voltage is always the same. So here the most important thing that you must know is that voltage is the same flowing through all the components in a parallel connection. Then since voltage is the same here, for us to find the total current, we are going to add our current 1 plus our current 2 plus our current 3 plus, if there is more, you're going to add more, plus your current 4 plus your current 5 if you have more current there. Then for you to find the total resistance, So there are two formulas that we use when finding the total resistance. You can either use total resistance. So there are two formulas. You can either use this one. So 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So you can continue adding if you have more resistance. Then you can also use this one. You can also say your total resistance is equal to the product of the resistance divided by the sum. So we can say R1 multiplied by R2 multiplied by R3 divided by R1 plus R2 plus R3. So these two formulas, this one and this one, they give the same answer. So you can use one, and let us do some of the simple calculations. And for this calculation, if we have this circuit in this form, so if this is the resistor, this is the resistor, and here the current that is flowing is 2 amps, and the current that is flowing here is 3 amps, and you have been told to calculate the total current. And as you can see, this is a parallel connection. So for us to calculate total current, we're going to say current 1 plus current 2. So our current 1, that's 2, plus our current 2, that's 3. So our answer is going to be 5 amps. Let us look at another example. So for this example, as you can see, we have two resistors. So here the resistor reads 2 ohms, and here it reads 4 ohms, and the electromotive force that is coming from the battery is 8 volts. And if you have been told to calculate current there, we can calculate the current. So you can calculate the current that is flowing through this resistor. So we can say our first current is equal to voltage divided by resistance, and we know that voltage is always the same in a parallel connection. So that's going to be 8 divided by 2, and 8 divided by 2, that's 4 amps. And for us to calculate our current 2, we're going to say voltage divided by resistance. Our voltage is always the same, so we're going to use 8 volts divided by our resistance 2 here. This was resistance 1, sorry, and this is resistance 2. Resistance 2 there is 4, so that's 2 amps. And for us to calculate our total current there, we're going to add current 1 plus current 2. So that is going to be 4 amps plus 2 amps. Our answer is going to be 6 amps. So from these all calculations, we can say for us to calculate our total current, if you have been given this setup, we can just say voltage divided by resistance 1 plus voltage divided by resistance 2. So that's the other formula that you can use. Let us look on how you can calculate the total resistance in a parallel connection. So with the total resistance, I gave two formulas. I said you can use this one. 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Or you can use this one, where you say the product of the resistors divided by their sum. And for example, if you have this setup, so if you have this setup and you have been told to calculate the total resistance there, we know that we say 1 over RT is equal to 1 over resistance 1 plus 1 over resistance 2. So that's going to be 1 over RT is equal to 1 over our resistance 1, that's 2, plus 1 over our resistance 2, that's 3. So that's going to be we can find our lowest common denominator there. Our lowest common denominator, that's 6. So 2 into 6, that's 3, plus 3 into 6, that's 2 into 6, that's 3 multiplied by 1, that's 3. Then 3 into 6, that's 2 multiplied by 1, that's 2. So as you can see, we're going to have 3 plus 2 is 5 divided by, that's going to be divided by 6. And from this, we can say we can cross multiply here. And if we cross multiply, we're going to have RT multiplied by 5. So we're going to have 5 RT is equal to 6 multiplied by 1, that's 6. So for me to calculate the total resistance, divide by 5 here, divide by 5. So I'll say my total resistance is going to be 6 divided by 5. So let us prove it by using the other formula that I had given. So the other formula, we're going to say total resistance goes to, we're going to multiply, divide by the sum. So resistance 1 multiplied by resistance 2 divided by resistance 1 plus resistance 2. So resistance 1, we know that's 2 multiplied by 3 divided by 2 plus 3. So here I'm going to have 2 multiplied by 3, that's 6, divided by, so this is ohms, divided by 2 plus 3, that's 5 ohms. So as you can see, this answer and that answer is the same. So you can decide on your own which formula that you want to use. Let us look at another instance. If you have a combination of parallel and series connection, then 2 ohms here, then I have 3 ohms, I have 1 ohm, I have 2 ohms here. And if I've been told to calculate the total resistance here, so I have two types of connections here. So 2 ohms and 3 ohms, they are connected in series, as you can see, and 1 ohm and 2 ohms, they are connected in what? In parallel. So for this, we can add this one and this one, since these are in series. And in series, we know that you get your total resistance by saying R1 plus R2. So this is going to be 2 ohms plus 3 ohms, and that's 5 ohms. And since we know that this is in what? In that's in what? In parallel connection. So I can just use this formula. I can say total resistance goes to resistance 1 multiplied by resistance 2 divided by resistance 1 plus resistance 2. So that's going to be 1 multiplied by 2 divided by 1 plus 2. So 1 multiplied by 2, that's 2 divided by 1 plus 2, that's 3. And if I use the calculator there, I'm going to have 0.7 ohms if I round off to 1 decimal place. And for me to calculate the total resistance for this circuit, I'll just say 5 ohms that I had calculated at first plus 0.7 ohms. So my total resistance there is going to be 5.7 ohms. So those are some of the calculations that you can do under parallel connection. Where you have questions, you can ask in the group. Let us now look at the cost of electricity. So as you know, the electricity that we use in our homes, we pay for it. And here in Zambia, we use ZESCO. And if you have been given the ZESCO units, the units, they're going to be in kilowatt hour. So these are the units of electricity, and you need to pay for them. And we know that from our previous formula, we said power is equal to energy divided by time. And since we defined power is equal to the rate of work done, and from this we can say the units of energy there, it's the units of energy is joule divided by the units of time there, it's second. So that is going to be joule per second. So we can say the watts there are equal to joule per second. So let us proceed. So we also know that we can use the formula here when we make E the subject to the formula there. So we are going to say E is equal to power multiplied by time there. And from this we can also say 1 kilowatt hour is equal to, since this is kilowatts, and 1 kilowatt is equals to 1000 watts. So this is going to be 1000 watts multiplied by time. Since it's in hours there, we know that when we convert 1 hour to seconds, we are going to have 3600 seconds. And if we do our calculations there, when you multiply, you're going to have 3,600,000. So you're going to have 3,600,000 watt. That's going to be watt seconds. And since we have that, then we know that our watt per second here. So from this formula, we know that this is watt, isn't it? And when we multiply it by time, so we're going to have watt seconds. So we can also say that 1 joule is equal to 1 watt 1 watt seconds there. And since we have done that, so we know that that's 3,600,000, and if we cancel out the zeros there, we're going to have 3600 kilojoules. So we know that 1 kilowatt hour is equal to 3,600 kilojoules. So we'll continue looking at cost of electricity. And last time we said the units of cost of electricity is kilowatt hour. That's the units that we said. We said the units are given in kilowatts hour. And from our units, we can say, for us to calculate the units, we can say power multiplied by time. But we need to take into consideration that here our power has to be in what? Kilowatts. So if you have been given the watts, you need to change them into what? Into kilowatts. Then our time here has to be in what? In hours. So if you have been given time in minutes or in seconds, you have to convert it into hours. So that's the formula of units. And for us to calculate the cost of the units, so cost of units, the cost of units, you're going to say cost per unit multiplied by the number of units that you're just from calculating. So cost per unit multiplied by the number of units that you need to find. So that's the formula. So let's just look at some of the examples. So the first example reads, calculate the cost of using a 1000 watt electric iron for 2 hours and 100 watt lamp for 10 hours. If the cost of electrical energy is 5 GUE per unit, 5 GUE per unit, which means kilowatt hour. So here we have been given two instances. So this is our example 1. And for this example 1, we have been given information for an electric iron. We have also been given information for a lamp. For an electric iron, it says it uses 1000 watts. Then it is used for a period of 2 hours. Then this one uses 100 watts. Then the time is the same, which is 2 hours. So we are supposed to calculate the cost of using an electric iron or a lamp. Then the cost per GUE. So the cost per unit, the cost per unit we have been given as 5 GUE. So to start with that of an electric iron, we are going to collect our data. We know that there our power, it's 1000 watts, and if we convert them into kilowatts, that's going to be 1 kilowatt. Then we know that our time is already in hours, which is 2 hours. So we are supposed to calculate the units, and we know that when calculating the units, we multiply power multiplied by time. So our power, that's 1 multiplied by 2. So there the units will be 2 kilowatt hour. So our units will be 2 kilowatts hour. Since we have calculated our units, we can say the cost of using the electric iron is equal to cost per unit we have been given as 5 ngwe. So 5 multiplied by the units we had calculated as 2 kilometer hour, so multiplied by 2. So 5 multiplied by 2, that's 10 ngwe. So that would be the cost of using an electric iron. Let us look at the cost of using a lamp. So for the lamp, the power that we have been given is 100 watts. And if we convert that into kilowatts, that's going to be 0.1 kilowatts. That's going to be 0.1 kilowatts. Then our time, we know that's 2. Our time, we know that's 2 hours. So to calculate there for us, to our time, sorry, let me just see from the question. Our time, what time have we been given? So from the question it reads, and 100 watts lamp for 10 hours. So the time there, it's 10. So the time is not the same, sorry about that. So even here the time was supposed to be 10. So this is used for 10 hours. So let us change our time here. Time is supposed to be 10 hours. And for us to calculate the units, we are going to say power multiplied by time. Power is 0.1 multiplied by time, which is 10. So the units there will be 1 kilowatt hour. And since we have 1 kilowatt hour as our units, we can calculate the cost of using a lamp. So the cost will be equal to cost per unit, that's 5 ngwe, multiplied by the units that we have calculated, is 1 kilowatt hour. So the cost there is going to be 5 ngwe. Let us look at another example. So the other example reads, a television set of power 100 watts is switched on every day for 5 hours. What is the cost of electricity of 1 unit, which is kilowatt hour? A television set of power 100 watts is switched on every day for 5 hours. What is the cost of electricity if 1 unit, which is kilowatts hour, costs 12 kwacha? So for this one, we have been given a television set, and the power that we have been given is that it uses 100 watts. So if we convert that into kilowatts, we're going to have 0.1 kilowatts. Then we also know that the time, it is used for a period of 5 hours. Then the cost per unit, so cost per unit, we have been given as 12. So for us to calculate that, let us calculate the units. So our units here, we're going to say power multiplied by time. So power is supposed to be in kilowatts, so 0.1 kilowatts multiplied by 5. So our answer is going to be 0.5 kilowatts hour. And since we have that, we can calculate the cost. So cost is equals to cost per unit, which is 12 multiplied by the units, so 0.5. And if you do your multiplication there, the answer is going to be 6 kwacha. So you'll be paying 6 kwacha for using a television set that has a power of 100 watts if it is switched on for 5 hours every day. So that's the cost of electricity. Where you have questions, you can ask in the group. Let us look at the 3-pin plug. So we continue looking at electricity, and we're going to look at the 3-pin plug. So the 3-pin plug, this is the device which is used to supply electricity to an electric appliance safely. So this just supplies electricity to an electrical appliance safely. And this 3-pin plug is made up of 3 pins. That's why its name is it's called the 3-pin plug, because it's made up of the 3 pins. Also, the thing that you must know on this pin plug is that it is made up of 3 wires. It is made up of the live wire. It is made up of the earth wire and the neutral wire. So each wire here has to be connected to the collect pin in the plug. So when you're connecting these wires, they need to be at the collect pin. If they're not on the correct pin, your electric appliance won't work. So the 3-pin plug can be drawn in this form. So this can be our 3-pin plug. So the wire that is near the fuse, this is the live wire. This is the live wire. Then this can be our fuse. So this can be 5 amps. It can be marked 5 amps. So this is our fuse. Then the wire that comes on top is the earth wire. So the earth wire. Then this wire is the neutral wire. So as you can see from this pin plug, we have 3 pins. We have this pin, we have the other pin on the live wire, and the other pin on the earth wire. So each wire, as you are connecting, it has to be placed on a collect pin. If you don't place it on a collect pin, your electric appliance won't work. Let us look at the functions of each wire. So we're going to look at the function and the color of each wire. So we're going to start with the live wire. So the live wire can either be red or brown in color. So this can either be red or brown in color. Then the live wire supplies current from the main supply to an electric appliance. So this supplies current from the main supply to the electric appliance. So these supply current from the main supply to the electric appliance. So that's the function of the live wire. Let us look at the neutral wire. So the neutral wire can either be black or blue in color. So it can either be black or blue in color. Then this is used to complete the circuit. So the neutral wire is used to complete the circuit. And the neutral wire, it has approximately 0 voltage. So this has approximately 0 voltage. Then the other thing that you must know on the neutral wire is that the neutral wire is the route of electrical current taken when leaving the appliance. So when current is leaving the appliance, the route that it uses is the neutral wire. So this is the route taken by current to leave the appliance, to leave the electrical appliance. Let us look at the earth wire. So the earth wire can either have a green or a yellow color. So it can either have a green or a yellow color. Then the earth wire is connected from the appliance to the ground. Then at some point the earth wire provides some safe route for the current in case of the live wire touches the casing of the appliance. So in case the live wire touches the casing of the appliance, the earth wire is going to provide some safety. Then the other function of the earth wire is that the earth wire prevents a user from electrical shock. So this prevents the user from electrical shock. So that's all about the 3-pin plug. Let us look at the 2-pin plug. So the 2-pin plug, as the name suggests, that means it only has 2 pins. And the other thing is that this only has 2 wires, and the wires that it has is the live wire and the neutral wire. And this 2-pin plug is used by electrical appliance whose outer casing is made up of an insulator. And examples of these appliances, we have radio and the blower. So we have the radio and the blower. So the 3-pin plug is used by electrical appliances that has the outer casing or the cover that is made up of an insulator. So if the outer casing is made up of an insulator, the pin plug that is going to be used is a 2-pin plug. Let us look at the fuse. So the fuse, this is the device consisting of a chip or a wire which melts and breaks on electric current if the current exceeds safe level. So a fuse, this is just a device consisting of a chip or a wire which melts and breaks on electric circuit if the current exceeds a safe level. And from our drawing, we said it looks in this form. Then it is connected near the live wire here. That's where you can find the fuse. So this consists of a chip or a wire which will melt when current that is flowing through the electrical appliance exceeds a certain level. So that's the definition of the fuse. So some of the elements that you can use to make the fuse, you can use copper. You can use copper. You can use silver. You can use aluminium. You can use alloys. So these are some of the materials that you can use to form a fuse. And here it must be known that copper is not mostly used because it has a high melting point. So copper is not mostly used because it has a high melting point. Let us look at how a fuse works. So let us look at how a fuse works. So a fuse works in this form. So when a high current flows through the circuit due to overloading or a short circuit, the element rises to a high temperature. That means that it's going to get heated and it will melt. So it can melt directly, or it can melt a joint within a fuse, and when it melts, that means that the circuit is going to be open. And when the circuit is going to be open, that means that current won't flow through that appliance. And we need to also know the materials that are used for a fuse to be made. So the materials that are used must have the following characteristics: must have low melting, must have low melting point, then they must also have a low resistance. The other characteristic is that they must have a high conductivity. So a high conductivity, and must have a low cost. So these are some of the properties that the element must possess for it to be formed as a fuse. Let us look at the factors that can make a fuse to blow. So factors that can affect the fuse to blow. So the first factor is if we have a short circuit due to bare conductors. So short circuit due to bare conductors, that's the first factor. The second factor is that if you have overloading of a circuit. Then the other factor is that using a fuse of the long rating. Then the other factor can be using a fault fuse or a damaged fuse. So those are the factors that can make a fuse to blow. Let us look at what happens when you are using a small fuse for a big appliance. So you are using a small fuse for a big appliance. So if you're using a small fuse for a big appliance, the fuse will blow off because of receiving a high current. So if you're using a big appliance and you put your fuse, which is of a small rating, that fuse is going to blow up because of high current. Let us look at another instance using a big fuse for a small appliance. Let's look at another instance using a big fuse for a small appliance. So the thing that's going to happen is that the fuse will not protect the appliance from excess current, and you may put yourself, your home, or your life at risk. So that means that the fuse will not protect the appliance and the appliance can burn down. Let us look at the fuse marking. Let us look at fuse lighting. So most of the fuse, are going to discover that they are marked on the body or on the end of the caps. Then the fuse rating depends on the current required by the appliance. So let us look at some of the examples. So I have this example, and the first example reads: a refrigerator operates at 160 watts, 240 voltage. So I have 160 watts, 240 watt voltage. Then the question proceeds: which is the most suitable fuse for the appliance? So the fuse that have been given a fuse that is marked 2 amps, the other fuse that is marked 5 amps, the other fuse that is marked 10 amps, then the other fuse that is marked 15 amps. So here the first thing that I'm going to do is to calculate current. And when I calculate current, I need to get the fuse that is going to have a higher current than the current that I've found, but that fuse must just have a small difference. The difference must not be that big. And since we have been given power and voltage, and we know the formula of power is equal to voltage multiplied by current. So to make current the subject of the formula, I'm going to divide by voltage. So current is equals to power divided by voltage, and my power there have been given as 160 watts divided by voltage have been given 240. So my current there is going to be 160 divided by 240, that's 0.1. So I have 0.1 amps. So from these fuse marking or fuse rating, the most suitable one that I'm going to get is 2, because this is 2 amps is near to 0.1 and it is greater. So the fuse rating that I'm going to get is 2 amps, and that means that we are done with electricity. Where you have questions, you can ask in the group. So at Just Production, we provide the following services. We sell some past papers with answers. And the past papers that we have 2017, 2018, 2019, and 2020. And these past papers, you can get them at both hard copy and soft copy. For the soft copies, they are only going at 20 kwacha per paper. So that means if you want paper 1 for 2020, you just pay a 20 kwacha. And after you pay 20 kwacha using Airtel or MTN mobile money, we're going to send it on WhatsApp. Then if you want a hard copy, it is free delivery within Mandef constituency, or we can deliver in town, we can meet in town, and I can give you that hard copy. Then the other service that we provide at Just Productions, that we provide online tuitions. And for the online tuitions, we provide subjects like physics, chemistry, math, and biology. And the price is only 100 kwacha per subject. And for instance, if you want to be learning mathematics, you just pay 100 kwacha, and you are going to be added to a WhatsApp group. And in those WhatsApp group, we actually post videos on a particular topic, and where you have questions, you can ask in the group. So that's how the online tuitions work. So it's 100 kwacha per month, and that's per subject. Then we also sell some books. We sell books for all the grades from grade 10 to grade 12. And these books include for physics, chemistry, math, and biology. And the price is only 10 kwacha per subject, and that's soft copy. And for the hard copies, it's only 25 kwacha. So for further information, you can call me or text me on the number that is showing on the screen, which is 0973023620. Peace. God bless you. The full topic of current electricity is available, and it's only going for sale at 10 kwacha. And after you make a payment using Airtel or MTN mobile money, I'm going to send the video on WhatsApp, and this video includes the following: electrical symbols, current, quantity of charge, direction of current, potential difference, electromotive force, electrical energy, power, electrical resistance, the circuit, series connection, parallel connection, cost of electricity, the 3-pin plug, the fuse.